So now, based on this model of force equals mass times acceleration, we're essentially going to assume a couple of forces. We're going to assume the force caused by the mass, so the force of the mass, and our assumption is that the mass always the force. There's always a counter force of the mass in the opposite direction of where it's going. So the mass is moving this way, but there's a counter force going this way, which is the result of gravity. Now, gravity, we know, is, again, mass times acceleration, except in this case it's the mass of the actual, whatever you want to call this, the mass of the mass, and the acceleration is the acceleration due to gravity, typically 9.8 meters per second squared. And so we can resolve this force vector right here by first of all observing that this is a vertical line here corresponding to this angle, and so as it turns out, because this line is just an extension of this shorter angle here, that means this angle here is theta, which by some geometry, if this line here is parallel to this line here, then this is also theta, which means that this length is actually, well, there's the right angle. So if we take sine of theta, that's going to equal this side over this side. And to solve for this side, we would multiply by mg, and so we would get mg sine of theta, which is the magnitude of that force right there. Okay, and then we're also going to assume damping force, which could be wind resistance, any types of friction. Friction up here can be accounted for by an extra term. And so here is our first force term, and that's of course negative because it's an opposing force, and also that's opposing the angle. So if we're moving in this direction, then the force is back in this direction. And we've also always assumed that damping force is negatively proportional to the velocity. That, in other words, it slows down or it alters the velocity, and that's equal to mass times acceleration. Well, what acceleration are we referring to? We're referring to the acceleration of the arc length. Well, that is equal to, the acceleration is equal to the mass times the acceleration, and in this case we have the mass times the acceleration of the arc length. Now, if we collect some terms here, we get the following: mass times length of the rod times the acceleration plus the damping term plus the force due to the mass. Okay, and so this is actually a second order nonlinear ODE because of the fact that we have constants here, we have a constant there. Now, it's not so much that we don't have a constant here that creates the problem, but it's not simply mg theta, it's mg times the sine of theta, which makes that a nonlinear function on the dependent variable. Now, theta is the same thing as we've been using in the past. We could call it y, so sine of y would make this thing nonlinear. Well, how do we analyze such a model? It turns out that what we can do is we can decompose any second order DE into a system of two two first order ODEs. I shouldn't say linear because it won't necessarily be linear, so first order ODEs. And it turns out that the trick here is to assign a variable to the first derivative. So by letting v equal d theta dt, what I can do is I can make a substitution here. Also, what I know is that dv dt in that case is equal to the derivative of theta with respect to t, the derivative of that, which is the second derivative of theta with respect to t. And so this allows me to make some substitution. So wherever I see the second derivative, I'm going to replace it with dv dt. So my model up here becomes dv dt plus b over ml d theta dt. Well, d theta dt is simply v by my substitution, and I have plus g over ml times sine of theta equals 0. Okay, so I actually already have one differential equation, and that was based on my substitution here. So my first equation in this system is d theta dt equals v. And my second model, if I now solve for dv dt, is dv dt equals negative b over ml times v minus g over ml times sine of theta. And so now if you look at this system, d theta dt and dv dt, then that system can be written as, let's see, the coefficient of theta is 0, the coefficient of v is 1, the coefficient of down here, v is negative b over ml, and the coefficient of, in this case, sine of theta is g over ml. But here's the problem. Because this is a nonlinear dE, I actually cannot write this as a function of theta and v. So my problem here lies in the fact that sorry, I should actually have these switched. This is the coefficient of v, this is the coefficient of theta. So it's not just negative g over ml times theta, it's negative g over ml times sine of theta. So unfortunately, I can't write this as a first order differential equation, a first order linear differential equation, to be specific. So what I can do is first of all think about the equilibrium points of this function. So for simplicity, let's assume that b over ml and g over ml equal 1. So that allows me to write d theta dt if g equals m equals l equals 1. Then what I get is d theta dt. Let me back up here a second. D theta dt equals, well, that doesn't change. It's just going to be 1v. But dv dt will simplify because it has all of those constants in it. So if I assume that b over ml and g over ml are equal to 1, then what I have is I have negative v minus sine theta. Negative 1v minus sine of theta. Okay, so now this just makes it a little simpler to think about equilibrium points. So first of all, under what condition will the first or second equation have a rate of change of 0? Well, it's pretty easy to see that if v equals 0, then d theta dt is equal to 0. There's no change. Okay, so if there's no initial velocity, then there is going to be no change in the angle. However, what will keep us from having a change in velocity is dv dt will equal 0 whenever negative v minus sine of theta is equal to 0. So that means that's going to be the case where, first of all, I have to make sure that v is 0 because that's the only way that d theta dt is going to be 0. So that means 0 equals 0 minus sine theta. So I need to ensure that sine of theta is equal to 0. Well, when is sine of theta equal to 0? Well, sine of theta is equal to 0 either when theta equals 0 or when theta is equal to pi. So let's think about this in the context of this pendulum. So this pendulum is hanging from a point, you have a mass, and its angle is exactly 0. Theta is equal to 0 when this mass is hanging straight down. So if there is no initial velocity and there is no initial angle, then the mass is not going to move. However, what does it mean for theta to be equal to pi? Well, pi would mean that the angle between this point and the vertical, that this angle here would be pi, theta equals pi, which means that this mass would be sitting on the end of this completely vertically, and assuming you could get this thing to be completely vertical, kind of a balancing game here, if you can get this thing to be completely vertical, then and there's no initial velocity, then in theory that would stay completely vertical. Now we can demonstrate this with our applet by showing if theta is equal to 0, then nothing is going to happen over time. We can see that the angle is not going to change at all. Now, unfortunately, I can't get this thing to be completely 180 degrees, so the closest I can get is just to get a quick snapshot. And you can almost see that if it were staying straight up without any initial velocity, then it would stay straight up. So that leads me to the equilibrium points of theta comma v equals 0, 0, or theta comma v equals pi 0. So those are my two equilibrium points for this system. Alright, so again, to review how we're going to now operate on this and try to linearize it, is we need to take the partial of the first function with respect to the first variable, and then with respect to the second variable, and then of the second function with respect to the first variable and the second variable. So I need to do some bookkeeping here. First of all, I need to rewrite my system as I have d theta dt is equal to v, and I have d v dt is equal to negative v minus sine of theta. Okay, so to keep this simple, if I want to use x and y, then I can do that. So dx dt is equal to y, where theta is x and v is y. And then dy dt would be, I'm going to write the sine component first. That's negative sine of x minus y. And so now the Jacobian matrix is going to require that I find the partial of x with respect to x. And, well, in terms of this function, dx dt equals y, y is a constant with respect to x, so its derivative is 0. And I don't need to evaluate it at my equilibrium point, pi comma 0, because, first of all, the rate of change is 0, regardless of what theta or v are. Now, the derivative of dx dt with respect to y is going to be 1, and that needs to be evaluated at the point pi 0. But we can see that regardless of what theta or v are, the derivative of x with respect to y is going to be 1. And I've got to do the same thing down here. The derivative of y with respect to x. Okay, well, wait a minute. Y is a constant, so the derivative of that term is 0. The derivative of negative sine of x is negative cosine of x. And now I do, in fact, need to evaluate it at the point pi 0. And now the derivative of this function with respect to y, well, that's a constant. Derivative of negative y is negative 1, and there's not much to evaluate there at the point pi 0. And so my Jacobian, with my points evaluated, well, negative cosine at pi cosine is at negative 1. Draw a quick cosine curve. Cosine looks like this. Here it is at pi. So the negative of negative 1 is positive 1. And then we have a negative 1 here. Okay, and so there's my Jacobian matrix. So that means my linearized system, system is going to be the Jacobian 0, 1, 1, negative 1 multiplied by the, I've got to go back for a second here, and we wrote these in the order theta v, so this has to be in the order theta v as well, which is equal to 0 theta plus v, 0 theta plus 1v, and then 1 theta minus 1v. And these are the equations for d theta dt and dv dt. Okay, so there's our system of differential equations that are now linearized. So again, what I can do is I can analyze these in phase plane and see how the behavior would be different at the point pi 0 or near the point pi 0 under the non-linearized version and the linearized version. So let's do that next.